Hi everyone. Since I'm attending a summer school this week, my time slot is full, so I will not be able to attend the tutor sessions. But I'm pre-recording the topic I'm going to talk about here. Okay. The topic is the dual challenge of search and coordination, and is for session 7, Organization 2.0. At the beginning, when Chen Wei introduced this session, he presented a graph of an organization structure, and he mentioned that there are different ways to design it, right? So I think it was a graph about a station where there's a manager and the other employees. And it's actually an observation that organizations increasingly use agile and flat designs to adapt quickly, and dismantling the traditional hierarchical structures. The paper I'm going to talk about today is with the title of The Dual Challenge of Search and Coordination for Organizational Adaptation, How Structures of Influence Matter. It's published in Organization Science, and it's actually, at first, this is a good journal, and this is a recent paper. The different structures of organizations actually affects how the employees pass on information to each other. And this paper's goal is to investigate how this information of how the structure influence this search and coordination challenges by passing on information by this mechanism, not mechanism, but by the employees passing on information to each other. First, what's the dual challenge? First is the search challenge, that the agents must explore a task environment to find superior actions with high payoffs. You can imagine there are different options, and the agents have to, maybe by trial and error and selecting the one yields the highest payoff during this process. But there's also a coordination challenge, that their actions are highly interdependent. The payoff of one agent's choice depends on what others agents simultaneously choose. When these two co-occur, then we're talking about coupled learning. The individual's learning is coupled to the rest of the team. The assumption here is that no single agent has superior wisdom to just dictate the right answer. To search, we need a task environment. This is a simulation, a research method. So in this setting, organization is consist of multiple individual agents, or a set of individual actions collectively makes up an organizational action. In a simulation setting, the authors sets the organization payoff as average of agents' payoff. The search challenge is that each agent faces several choice alternatives with different payoffs, as I just mentioned, but the payoff structure here is predetermined in a way that there's one choice randomly designated as the best possible option, actually with payoff 1, and there are actually 7 possible options to choose from. And the remaining options or choices have randomly distributed lower values. I forgot the distribution, maybe a normal distribution between drawn values between 0 and 1, or uniform distribution. And all the agents face the same structure. Now it's clear that the agent's goal is kind of trying to find this best option with payoff of 1, maybe through trial and error, trying the other options, and finally find this one and keep choosing this one when this one's found. This is kind of their goal in this structure. But there's also a coordination challenge. that the agents face a performance penalty if they fail to converge on mutually compatible options. In other words, the payoff of the option that the agent selected will have a penalty if this option is not simultaneously chosen by the other agents in this uh, in the same organization. So this is formulated mathematically that the payoff pi for agents I on choice k on this period t equals the value, right? The agents derived from this option k by multiplying this large weighting with which is, if this value multiplying something smaller than 1, then this is a penalty, you can see. This x parameter here models how important coordination is. And this is because the f kt means that the fraction of the other agents in the same organization choosing the same option k on period t. By formulated in this way, if x is large, then the fraction of choosing, if the fraction of choosing the same option is low, the whole penalty for this value on this option will be high. All right. I'll just repeat it again. This is just trying to model that the coordination is important in this task. So if the agents want to choose something that the other agents is also choosing, right? So if they choose something that is not, then the payoff they receive from choosing this option will decrease, will suffer from a penalty. That's all. And with the larger value of x, this penalty from coordination is higher. With the larger x, of course. And now we can talk about the multi-agent reinforcement learning. The basic idea of reinforcement learning is that you see the agents are choosing the options. Each option will give a payoff. The basic idea is if the payoff is kind of high, then the probability for the agent choosing the same payoff will increase. But if the payoff, I'm sorry, not choosing the same payoff, I mean choosing the same option will increase, right? Because the payoff is good. If the payoff is bad for a certain option, then the probability of choosing it will decrease and the agents will change to explore other options. So this is the basic idea for reinforcement learning. Now to determine the value or the payoff of a certain option, we have the belief for each agent and it's updating throughout this process. The belief for agent I for this option k on period t equals the belief, right? For this agent I on option k during period, actually the previous period t minus 1, multiplying something, I will talk about it, and then plus this new payoff when sampling or trying this new option for agent I on this new option, the same option actually, the same option k on time t. And this nijt is just a way the authors model the recency effects, meaning that since the nearly sampled options will be more salient, so they should have a higher weighting in terms of value compared with the ones that has been tried a long times ago. Of course, from a modeling perspective, we can remove this component, right? We don't have to include recency effects, but we can include it. It depends on your choice. So if we just ignore it, the belief of this option is actually the belief from the previous option, and if you try this option on period t, you get this payoff, right? You add this payoff onto your previous belief, and then it became the new belief, the current belief. That's all. It's not complicated at all, although it seems maybe it seems to be. right? So this is how agents updating belief. The past belief will get passed on, but it will change by updating the new payoff of the current option, and then it became the new belief. In this setting, each agent has a prior belief, which the initial belief drawn from a uniform distribution between 0 and 1 at the period t. Sorry, at the period 0 at the start, which is a value, so that there's a variety created between all these agents, so they don't behave in entirely the same way. I think that's the point. So they're kind of different between each other in an entirely random way, because this pair is drawn from a uniform distribution between 0 and 1, which is any value randomly drawn between 0 and 1. The important part here is actually the social influence that the belief for an agent I on time period t is not only depends on this agent alone, right? Because we already mentioned there's a coordination challenge, and beside this coordination challenge, there's also social influence because they're in the same organization. So this belief actually is influenced by the other agents in the same organization, modeled by this parameter W. So this W multiplying right, this individual belief of the agent plus 1 minus W, the other weighting, multiplying the belief from the other agents in the same organization. So you see this W is modeling how much the opinions of the other agents in the same organization matters. If W is high, close to 1 or even 1, means that the other agent's opinion doesn't matter, there's no social influence. But if W is low, then it's the other way around, meaning high social influence. The belief, individual belief, is highly affected by the other agent's belief. So you see, this is just a linear combination of both. There's also the decision rule, which we saw multiple times in previous tutor sessions, that it's just a logic choice rule. The loose decision-making rule we just saw before is just modeling this belief and squeezes into a value between 0 and 1, meaning that the option with higher belief will have a higher probability of being chosen. And that's all. So this is not deterministic. It's not the agent choosing every time the according to the belief which option the agent thinks the best. It's based on probability, but the probability of choosing the best one is the highest among all possible options, which I mean introducing some randomness because people actually don't behave in a deterministic way. Sometimes we want to try something else, maybe the second best. Not every time we want to try the best thing, but the probability of we trying the best thing is the highest. This is the idea of the loose decision-making rule, the logic transformation here, transforming the belief into a value between 0 and 1 as probability. Below here, we can already see 3 organizational structures. This affects the value of parameter W on the social influence one, and I'll just talk about it here. First is the crowd. We see the crowd is just each individual, and it acts independently, right, with 0 social influence on on each other's beliefs, right? It's just an atom in this case. So they only learn from the environment. So the W is 1. Go back here. If the W is 1, and 1 minus W will be 0, meaning that only the individual belief matters here. No social influence for the crowd. Each crowd acts on their own. I mean, each agent in the crowd acts on their own. On the contrary, we have the extreme case of flat team, which this is a fully connected symmetric network that every team member has an equal amount of influence on everyone else, and the weighting is set to be 0.5 here, meaning that the belief from the other members, other agents in the same organization has the same weighting of the individual belief, and you add them together for the belief, for this particular individual. So this is the flat team. Everyone is just simultaneously influencing each other. Last but not the least, we have the hierarchical team, a structure with an apex agent, the leader who has asymmetric influence over the other members, but not influenced by them in return. You see this agent in the middle is diffusing its belief to the other agents, right? Because this is a hierarchical structure. So this agent can think is the leader and it's just influencing the other agents, but the other agents do not influence this leader. But the other agents are influencing each other. So this leader actually behaves like an agent in the crowd, right? Because you see here, the leader's W is said to be 1, with the leader acts on its own, but the other members here acts like the flat team, right? Because the other agents are influencing each other, but not the leader. Right? So the others agents in this hierarchical team is set with a W of 0.5, is same as the flat team. And this is how the social influence of belief is set. Now we can look at the results. The first thing I want to talk about is the observation that hierarchical structure wins in the short term, which is the top row here. We should first read below. The dominant structure is indicated by color, so the flat team is green, the hierarchical team is red, the crowd is blue. The depth of a shade shows the magnitude of advantage over next best structure. With more color, intuitively meaning that it's more dominant. And we have 9 different groups here. On the y-axis is the time length. So t equals to 50, meaning that is a short time frame. Then t equals to 100, meaning it's a longer one. The length equals to 500, meaning it's a long run. So short run and long run for the y-axis. For the x-axis is the x parameter I just talked about, meaning that how important is coordination in this task. Higher the x, the more important. So in x equals to 1.0 on the right-hand side, this column is where the coordination is most important, and that the agents will be penalized. Their payoff is penalized by not choosing the option that the other agents are choosing. And of course, on the left-hand side, this column with x is equal to 0 here is where coordination doesn't matter. They're not penalized by not choosing something the others are choosing. As I mentioned, the first observation is on the top right, where t equals to 50 and x equals to 1, we see that the hierarchical team won. And we want to talk about why. And even it won a proportion in a slightly longer t equals to 100 and x equals to 1 scenario. So why the hierarchical team won in the short term? No, hierarchical structure, not team. It's because team. No, it's no team. Okay. Yeah, the results we observe is that it achieved the highest and most rapid degree of convergence. Here, so the convergence is the agents successfully select the same exact action at a given time, and we see that the hierarchical team is actually orange in this case, right? So if we fix the x-axis, we can see throughout the whole length of time, the hierarchical, the orange line is always on top of the other ones, meaning that the rate of convergence is always highest for the hierarchical team. Right. So they're choosing the same thing. Here. And the mechanism is that hierarchies create beliefs that are both similar and have high resolution. I can talk about the anchor effect first. Because the apex leader is resistant to influence, their behavior stays relatively stable, which prevents uncoordinated simultaneously exploration and gives the team an anchor to coordinate around. This relates to the mechanism I just talked about. It's because you see this apex leader is resistant to influence, but it's diffusing its belief to the rest of the agents. So the agents will become more and more similar to the leader throughout the trial. Right. As they're more similar, the beliefs will become more similar and have high resolution. What does this mean? We can look at the resolution here. I think we should ignore the first tip because I think it's because at the start of the task, everything is not stable. The agents are exploring, but after this, we can see that the hierarchical team have the higher resolution, right? So what does resolution mean? Is that you see the difference between how strongly they prefer their top choice versus their least favorite choice. We can obviously see that the resolution for the hierarchical team is much higher than the flat team and higher than the crowd in the initial rounds, meaning that um, their belief is very clear that, for example, option one is greatly better than, for example, option four. On the other hand, if the belief, if the resolution is low, then the agents are ambiguous between the options. The options seem all very similar to them, right? So choosing any of them will be arbitrary because every options look the same. This is the low resolution case. If it's high resolution, then it's clear that one option is better than the other. So why is this the case? Of course, it's because the apex leader is influencing the rest of the agents in the same organization, and they become more similar. And since the apex leader is uh, learning the task alone, then it will build up its own belief, which has a high resolution. And since the other agents are largely affected by this high resolution belief, their belief, or the organization's belief as a whole will have a high resolution. All right. So we see a high degree of convergence because this is the same, right? They are influenced by the same apex leader. So after a short period of rounds, they're going to be picking the same options because they're becoming more similar to the apex leader. Then their convergence of the options, of course, will be high. This is the reason why hierarchy wins in the short term. Is because if we look at this right column where coordination is important and the agents is penalized by not choosing the same options, since the apex leader is diffusing the belief to the other agents and they become similar to the apex leader, then they're choosing the same thing, meaning high resolution, high convergence, then they're not penalized. So their performance will be high in the short run, right? Because they're choosing the same thing, then of course the organization performance with all these individual payoffs add up will be high because every one of them are not penalized in this x equals 1 where coordination is very important. However, it entails a trade-off that hierarchies are prone to getting trapped on good enough non-global peaks because they converge so fast. You can think of the apex leader is resistant to influence, but is uh, learning the task alone. So maybe this apex leader only tried no one, two, three options, and then the leader determined okay the second option to be the best, and then keep choosing it, diffusing this belief to the other agents, and the other agents are all choosing option two. But actually, since in this task, there's a best option, maybe is option six, then they're actually never going to try option six because the leader is not trying it. So that they're going to be trapped on the good enough non-global peaks of option two because they converge so fast. This is trade-off and why they lost in longer terms instead of a short term. The next observation is the exploration trap of flat teams, that the results we observe is that flat teams are dominant when there is no interdependence or pure parallel search, but they struggle when coordination is required, which means that on the left-hand side, right, the left column here, when coordination is not important, we can see it's all green. The flat team outperformed the other two structures, but when gradually coordination matters, is 0.5, gradually matters, 0.5 kind of matter, and we see the flat team is kind of winning. But then when it really matters, when x is set to 1, then the flat team is losing. So why couldn't the flat team uh, converge? Right. And although, right, the mechanism here is that they attain high similarity in beliefs, but the beliefs have very low resolution. Okay, so similarity is the no here, bottom left, we can see the similarity of the flat team is kind of the highest in initial rounds, right? So they're similar. Oh, so why they're similar, you can think of the network structure. Every agent is influencing the others, right? Simultaneously, and they're fully connected, meaning that they're all become similar to each other, similar to the hierarchical team. But in a hierarchical team, is the other agent becoming similar to the apex leader. But in the flat team, is every agent similar to each other. But this similarity actually is with a low resolution. As you can see on the top right, the resolution the flat team has lowest. And I can explain this. You see, for example, one agent maybe explored options 1, 2, 3, and this agent found that okay, option 2 is good. But the other agents maybe explored 4, 5, 6 and said, okay, option 5 is good. And you see, all these agents are influencing each other from their individual search. So what the belief, when they're aggregated, you get something like, okay, option 2, option 5, and maybe option 6, option 7 are all great. And you see the resolution is low because every options are kind of great, and it's not possible to distinguish one from the other. What happened in this case is that since all options look similar, right, then choosing any of them wouldn't matter. You just arbitrarily pick one, and so you see there's a large room for exploration. Sometimes you choose option 2 because it's kind of good. Sometimes you choose option 5 because it's kind of good. This causes the high instability here that you see the flat team has the highest instability, right? So they're just frequently switching their chosen options from period to period because the resolution is low, because every options look similar to them. So I already talked about the mechanism, and this causes excessive exploration, right? Because they're always changing um, the options to choose from. Everyone's constantly influencing everyone else, so they overexplore and they find it difficult to settle down and decide what option is actually the best among all of them. and leading to this instability. So that's why um, they do not perform well when coordination matters because they never settle down. As I just mentioned in my example, option 2567 is all grades, then all the options, sorry, all the agents will just randomly choose from these good ones. But when they're randomly exploring, they're not going to coordinate on choosing the best one. Then they're just suffering from this um, penalty in the scenario that coordination actually is important. So you see when X is set to 1, flat team never outperforms. But when this coordination doesn't matter, it actually creates kind of a good results, right? Because they're actually sharing the information within the system, right? Instead of like the um, hierarchical team is only like influenced by the apex leader. That's only one agent influencing the others, and the information is limited in this case. So it doesn't outperform the flat team in this situation um, where coordination doesn't matter. And also the crowd is also working on their own, right? Because they're not influenced by the social influence. So there's no information sharing in the crowd also, right? So they're just working on their own. Then of course, working as a group will outperform these two structures when coordination doesn't matter. In the end, there's the third observation that crowds win the long game. We see in a scenario where coordination matters, the crowd eventually outperform the hierarchical team when the time length in the long run, right? But why is this the case? The mechanism here is that the crowds rely entirely on bottom-up convergence provided by environmental feedback, allowing them to develop high-resolution beliefs over time. In other words, the crowds, as an individual, each individual, they're learning the rule of environments. And by the setting of reinforcement learning agents, they will eventually learn the task. They're directly receiving the feedback from the environment, which means they're directly learning the rule that convergence matters. Since they're learning this rule, then they will adapt. Although it takes a long time, but they will eventually solve the game because this is what reinforcement learning agents are designed for. By this belief updating process, they'll eventually solve the game by choosing uh, the the option that yields the highest payoff and also high convergence. If this task environment says that okay, if you do not converge, then you will suffer a penalty. They will learn this rule. So actually, I personally do not buy into uh, this interpretation that the cross win the long game because I think this is what you naturally would get from a reinforcement learning model. But of course, their setting is like the crowds is each individual, and then they found these results. Of course, they're going to explain it in this way, but I just think this is just what you naturally get from this setting up this model. Okay, I'll still talk about the trade-off here. So of course, as I mentioned, they're designed this way. They'll eventually find the best optimal peaks and avoid, the trap of convergence because they're still exploring and learning from the task individually and learning the rule, right? So they will not be trapped at the local maximum. But of course, solving this task as a reinforcement learning agent still takes time, although it can be entirely solved. So it's incredibly slow for them to get there. So, but eventually they will solve the game. The takeaways is that the hierarchy provides stability, it helps teams to coordinate quickly, even if the leader lacks superior knowledge or direct control over actions. Okay, so this is one assumption this model makes, is that the leader has no superior knowledge, right? But of course, we can change this assumption by adding some parameters into this model, which is more maybe um more close to real life scenario that the leader um would generally be more competent, I would say, right? And we can see by adding this parameter whether it changed the results. This is something to do. But yeah, but even like the leader lacks superior knowledge, the structure itself just helps the team and to win in the short run we just saw. Yeah, by resisting the social influence, the leader acts as an anchor and prevents the team from engaging in endless and uncoordinated exploration. As the flat teams, right, they struggle with this coordination while they excel at independent tasks, right, because they're sharing the information together, but their belief are low resolution, right? Even though they kind of know, like for example, option two and option five is kind of good, they're just switching. They're not they're not going to settling on one best option for the whole organization. So it causes the team to overexplore and delaying their ability to align actions. I hope all is clear, and please do let me know if something is not clear, maybe in next week's tutor session, or just drop me an email. Thanks.